Well, hello everybody, Brian Malloy here, and today's video is going to be about eliminating copies, omitting copies. And the CTP reference page is called copy elision. So elision, to elide something means to omit it. I thought I'd look that word up. Let's see, I've never...
Allied.
Allied. There you go. Allied means to omit. That's the way I've always used the word and heard the word. So copy elision means eliminating copies. And prior to C++11, there were so many copies being generated, and I'm going to show you how many can be generated in a few moments, that the language developers said we got to do something about all these copies. And all of these copies grow out of the notion of value semantics. For example, the C++ containers in the standard C++ library use value semantics, and value is simply another word for copy. So let me show you some of the copy elision that can occur. So here I am returning an instance by value. So you would think, ordinarily you would think here's a default constructor, and here is a copy constructor. Copy elision says in a return statement, when the operand is an R value or an L value, it doesn't matter, that the compiler is obligated, it's obligated to omit any copy or move construction of the class. So that's pretty strong. And in fact, here it says even if you cascade these T of F and then make a copy. So we call F, I don't know what F does, but let's suppose it does something, and then you make a T, and then when you pass this T into this T, you would ordinarily get a copy constructor there. We're not going to get any of that, as I'm going to show you. So let me show you first. So what I have here, as you can see, is I'm going to turn those copy elisions off so that we see all the copies, but I've got to comment it out for now. So I thought what I'd show you first is return value optimization. When it elides copies in a return statement, it's called RVO, return value optimization. If you look on this page, you'll find return value optimization. There it is. Okay, so it's called, well, this is named return value optimization, which is different. RVO is return value optimization. NRVO is named return value optimization. I'll show you both of those in a moment, but this is an example of return value optimization. It doesn't have a name yet, in other words. Up here, I'm going to give it a name. In this case, it'll be NRVO, where it has a name. But let's just stick with this simple example here. So what we might expect is default, copy, and then destructor. We're not going to get that, though. Watch. All we're going to get is default destructor. Why? Because what happens here, it does use the default constructor right here, but it elides, it omits this copy. It comes back here, sits there. We don't do anything with it. It falls out of scope when we call the destructor. So we get a default and then a destructor. That's what happens, and that's because of return value optimization. Now, what you might expect. Let's turn let's turn this copy elision of constructors off. So now we get this, and there we have what we might expect. So we get default here, copy here. There it is, default and then copy. So we get default, copy, then the destructor of the default, and then it sits there, and we come here, and then we get another destructor. So this is what you would expect if there be in all versions of C++ prior to C++11, this is what you would expect: default, copy, destructor. However, with the advent of C++11 and the obligation of compiler writers to elide these copies, then what we get instead is much, and that's a lot. This is a big savings, really. It kind of can be a big savings. We get default destructor. So we get default here, and then it comes back here and it sits here, and then it hits that, and we get a destructor call. So that's return value optimization. So we're returning by value, but we're going to optimize out the copy. Now, what happens when we call named return value optimization? So let me just put, what did I put? NR, but let me just put an N here. Okay, so I get the right one, and then we added a 1. and I'll put this in the repository so you can play around with this. But now, what we would expect is here, we would expect a default, copy, destructor, nothing, nothing. But what are we going to get instead? We're going to get default, nothing, destructor. Okay, let's see if I'm right. Probably not. And there we get it, default destructor. So the default happens here. We return it by value, but that return value is optimized out, so it comes over here and then gets destroyed. Now this one's called named return value optimization because it has a name. Okay, and you know what I wanted to do before? I forgot to do this. Let me do this. I wanted to show you what happens. So if I do, let me do this just to show you the fact that these are elided all over the place. What I'm showing you right now is, did I pass it up? This one. So I'm going to show you an example of that kind of a thing. So what are we going to get? You would expect default, copy, 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 destructor, 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 destructor. But that's not what we're going to get. It's going to all be elided out. Look, we get default, destructor. So it just gets this default. It elides that copy, it elides that copy, and it elides that one. And then we get destructor. Now let me just turn it off to show you the neat little savings we get. Now let me just go ahead and compile this and run it. Let me start at the top. And you see we get all those copy. So we get, just like I said, we get default here, then copy, wait, default, copy, copy, and then we get another copy for the return value because it's returned by value, and then we get all these destructor, destructor, destructors from here, and then this destructor. So return value optimization and named return value optimizations are pretty helpful. And I've got some other examples here that are just about the same thing. Here we're going to get convert, destructor. You can run it and see. And here I was going to turn these off, but I've already done it, so you get the idea here. Now what I do want to show you then, let me just see. Let me get rid of these again. I want to show you that about a move. Okay, so let me also get rid of these. Okay, let me go back to this. Now what I have up here is okay, so I'm just going to try to motivate move semantics. So what I have here is a move constructor, and what I have here is a move assignment operator. So what we had before was the usual, here's the usual copy constructor, and here's the copy assignment operator. But what I'm going to show you is something a little different, as try to, and maybe this isn't a good example of the motivation, but now let's see, and let's turn this off. I thought I'd start. Let's turn these off. Okay, so now let me. Oh, maybe I'm doing this the hard way, aren't I? Let me leave these. Let me go ahead and comment these out. So we don't have any move operations, which means they're not going to be automatically generated by the compiler because we've written the other three. So if we write the other three, it's not going to write the remaining two in the rule of 5. So let's turn optimization off. I'm turning, so I don't want any copy elision to happen. So watch what I get. So let me start at the top, and what I get is default, copy, destructor, destructor. So I get default, copy, and then destructor of the copy, and then this gets destructed too. Now, what I want to do is turn on move and show you that if we didn't have return value optimization, and I'll show you some better examples to motivate move semantics. But I thought I'd just segue into this at the end of this video. Now we have move operations, and by the way, just to let you know, this is the normal signature for the move constructor. That is ampersand. Ampersand means we're expecting an R value reference. And in this move assignment operator, we're expecting an R value reference. What's an R value reference? Well, one good example of an R value reference is a compiler generated copy. And a compiler generated temporary, I mean. And when you turn this off, ordinarily we'd get a compiler generated temporary as the return value. But now what we're going to get, instead of this copy, we're going to get default move destructor. So watch. Okay, so what we get is default move constructor, destructor. Now, what am I trying to show you here? I'm trying to show you that in many cases, not all cases, but in many cases, the move constructor is more efficient than the copy constructor. Okay, I'm trying to, let's just assume that that's the case. It's not always the case, but I'm going to show you some move semantics in subsequent videos. But let's just assume for now, and it will be in the string example, let's assume that the move constructor is more efficient than the copy constructor. Then I would say that in the absence of copy elision, and there are times when copy elision won't apply, and I will look at some of those, move semantics can be a savings over the copy. Okay, so that's my point. So what we need to talk about next is L values, R value references, move constructors, move assignment operators, and the rule of 5. We'll be segueing into the rule of 5 and show you that the golden rule is the rule of 3 will keep your program from crashing. The rule of 5 will keep your program from making some unnecessary copies. And that's what move semantics does. It's basically a pointer swap usually instead of a copy. So anyway, that's kind of an introduction to return value optimization. Here's the return value optimization and named return value optimization right here. I hope that helps. Really, for more of this, I'd go to this page and read all of this. Try to figure, and I've read this whole page. It ain't easy trying to find an example where it doesn't do copy elision. So these are all the examples when it does do a lot of examples when it does do copy elisions. You might want to read this page and try to find an example when it does not do copy elision. So, hey, happy programming. Brian Malloy, over and out.